Welcome to the lesson on trigonometric substitutions. In finding the area of a circle or an ellipse, an integral of the form integral of the square root of a squared minus x squared dx arises, where of course the a is bigger than 0. If it were the integral of simply x the square root of a squared minus x squared dx, the substitution of u equals a squared minus x squared would be effective. But as it stands, this first integral that we have here is more difficult. If we change the variable from x to theta by the substitution x equals a sine of theta, then the identity of 1 minus the sine squared of theta equals the cosine squared of theta allows us to get rid of the root sign, because if we take the square root of a squared minus x squared, we can rewrite this to be the square root of a squared minus a squared sine squared of theta, which becomes the square root of a squared into 1 minus the sine squared of theta, which becomes the square root of a squared cosine squared of theta, which becomes a, the absolute value of cosine of theta. Notice the difference between the substitution of u equals a squared minus x squared, in which the new variable is a function of the old one, and the substitution that x equals a sine of theta. The old variable is a function of the new one. In general, we make a substitution of the form x equals g of t by using the substitution rule, but backwards. To make our calculation simple, we assume that g has an inverse function, that is, g is 1 to 1. In this case, if we replace u by x and x by t in the substitution rule, we're going to simply obtain the integral of f of x dx equals the integral of f of g of t times g prime of t dt. This kind of substitution is called inverse substitution. We can make the inverse substitution of x equals a the sine of theta, provided that it defines a one-to-one function. This can be accomplished by restricting theta to lie in the interval between negative pi over 2 to pi over 2. Now, in the table that we're going to present on the next slide, we list the trigonometric substitutions that are effective for the given radical expressions because of the specified trigonometric identities. In each case, the restriction on theta is imposed to ensure that the function that defines the substitution is 1 to 1. So I'm going to break this up into the expression, the substitution, and then the identity. So if we have an expression, the square root of a squared minus x squared, our substitution will be x equals a the sine of theta, provided that the theta is between negative pi over 2 to pi over 2. And the identity that we're going to use is 1 minus the sine squared of theta equals cosine squared of theta. If we have the square root of a squared plus x squared, then this, our substitution will be x equals a tangent of theta, provided that the theta is between negative pi over 2 to pi over 2. And the identity that we're going to use for this is 1 plus the tangent squared of theta equals secant squared of theta. And lastly, if we have the square root of x squared minus a squared, our substitution will be x equals a, the secant of theta, provided that the theta is between 0, including 0, strictly less than pi over 2, or that theta is between pi, including pi, but strictly less than 3 pi over 2. And the identity will be secant squared of theta minus 1 equals tangent squared of theta. Okay, so let's take a look at an example. So let's suppose we want to find the integral of the square root of 9 minus x squared over x squared dx. Well, let's let x be equal to 3 the sine of theta, provided that the theta is between negative pi over 2 and pi over 2. Then what we can say is that our dx is going to be equal to 3 cosine of x, cosine of theta d theta. And what we can say is that the square root of 9 minus x squared is going to be equal to the square root of 9 minus 9 sine squared of theta, which is simply going to be equal to the square root of 9 into 1 minus sine squared of theta, which will simply be equal to the square root of 9 cosine squared of theta, which is the same as saying 3 the absolute value of cosine of theta, which is going to be 3 the cosine of theta. Note that the cosine of theta is bigger or equal to 0 because negative pi over 2 to pi over 2, that's where theta is going to lie. Thus, the inverse substitution rule is going to give us that this integral becomes the integral of 3 cosine of theta over 9 times sine squared of theta times 3 cosine theta d theta. That's what everything substituted back in. Okay. So now what we can say is that this becomes the integral of simply cosine squared of theta over sine squared of theta d theta. This becomes the integral of the cotangent squared of theta d theta. Now, how do we integrate the cotangent squared of theta? Well, let me just rewrite this here. We have the integral of the cotangent squared of theta d theta, we can use the identity that this becomes the integral of the cosecant squared of theta minus 1 d theta. And of course the antiderivative of the cosecant squared of theta simply becomes negative cotangent of theta. So we're going to get negative cotangent of theta minus theta plus an arbitrary constant of c. Now since this is an indefinite integral, we must return to the original variable x. This can be done either by using trigonometric identities to express the cotangent theta in terms of sine of theta, which is equal to x over 3, or by drawing a diagram where theta is interpreted as an angle of a right triangle. So let's draw a right triangle, and let's label this as being our theta. This becomes 3 and x, because remember the sine of theta is equal to x over 3. That was our initial substitution. And if we label this side using Pythagorean theorem, this simply becomes the square root of 9 minus x squared. So we can say that the cotangent of this angle theta is simply going to be equal to the square root of 9 minus x squared all over x. Although theta is strictly bigger than 0 in the diagram, this expression for the cotangent of theta is valid even when the theta is less than 0. Since the sine of theta is equal to x over 3, we have that sine of theta is equal to x over 3. We have that theta is equal to the sine inverse of x over 3. And so the final answer for this will be negative the square root of 9 minus x squared over x minus the sine inverse of x over 3 plus an arbitrary constant of c. Let's take a look at another example. So let's say we wanted to find the integral of 1 over x squared, the square root of x squared plus 4 dx. Here, let's let x be equal to 2 tangent of theta, where the theta is between negative pi over 2 to pi over 2, not including negative pi over 2 and pi over 2. So therefore dx will simply be equal to 2 the secant squared of theta d theta. And this x squared plus 4, we can rewrite this to be the square root of 4 tangent squared of theta plus 4, which is equal to 4 into tangent squared of theta plus 1, which is equal to the square root of 4 the secant squared of theta, which is equal to 2 the absolute value of secant of theta, which is equal to secant theta. So thus we have, when we substitute everything back in, this is going to be the integral of 2 secant squared of theta d theta all over 4 tangent squared of theta times 2 secant of theta. Which this is going to be equal to 1/4 the integral of secant of theta, or tangent squared of theta, d theta. Now to evaluate this integral, we put everything in terms of sines and cosines. Let me go to a next slide for this. We have secant of theta over tan squared of theta. Well, this is equal to 1 over the cosine of theta times cosine squared of theta over sine squared of theta, which this is equal to cosine of theta over sine squared of theta. Therefore, making the substitution where u equals the sine of theta, we're going to have 1/4 the integral of cosine theta over sine squared of theta d theta is going to be equal to 1/4 the integral of du over u squared. This, of course, becomes 1/4 times -1 over u plus an arbitrary constant of c. The u was, of course, the sine of theta. So this is simply going to be -1 over 4 the sine of theta plus an arbitrary constant of c, which this is the same as saying negative the cosecant of theta over 4 plus your arbitrary constant of c. Now we need to put everything back in terms of x. So let's use a right triangle again. So there's a right triangle. Here's my theta. This side I know is 2. This side I know is x because I have the property that tangent of theta is equal to x over 2. That was our original substitution. So this side, by Pythagorean theorem, is going to be equal to x squared plus 4. So the cosecant of theta is simply going to be equal to the square root of x squared plus 4 all over x. And so what we're going to get is the integral of dx over x squared, the square root of x squared plus 4, is simply going to be equal to negative the square root of x squared plus 4 all over 4x plus an arbitrary constant of c. Okay, let's take a look at one more example. Now, if we recall this example that we looked at in class, we were taking a look at the arc length of a segment of the parabola y equals x squared on the interval between 0 and 2. And in class we got that we have to find the integral between 0 and 2 of the square root of 1 plus 4x squared dx. Well, to find what this is, we need to do a trigonometric substitution. That's why in class I said at the moment back then, when we first took a look at arc length, we couldn't find it because we didn't know trigonometric substitutions. But now let's figure out how to actually solve this. I'm going to take the original integral and I'm going to write it this way. I'm going to say this is equal to 2, the integral between 0 and 2, of the square root of 1/4 plus x squared dx. That's just by taking out a factor of 4 from the square root, which this is the same as saying 2 the integral between 0 and 2 of the square root of 1/2 squared plus x squared dx. Now the integral contains an expression a squared plus x squared, with a equals 1/2, which suggests that our substitution of x equals 1/2 the tangent of theta should be made. It follows that dx should be 1/2 the secant squared of theta d theta. And if we take the square root of 1/2 squared plus x squared, then this is equal to the square root of 1/2 squared plus 1/2 the tangent of theta squared, which of course is going to be equal to 1/2 the square root of 1 plus the tangent squared of theta. And we know that this becomes the secant of theta. So this is going to be equal to 1/2 the secant of theta. So let's see what this becomes. So this is going to be 2 the integral of 1/2 secant of theta times 1/2 secant squared of theta d theta. This, of course, right here is my dx. Okay, so now this simply becomes 1/2 the integral of secant cubed of theta d theta. Now we saw before, with integration by parts, that the secant cubed of theta simply becomes 1/2 the secant theta tangent of theta plus the natural log of the absolute value of secant theta plus tangent theta. With the extra half that we have, this will become 1/4 times the secant of theta tangent theta plus the natural log of the absolute value of the secant of theta plus the tangent of theta. And of course we're integrating this between 0 and 2, but I left out the limits of integration because we still have to rewrite everything to be all in terms of x. So let's see what this thing turns out to be. So using a reference triangle, we express the antiderivative in terms of the original variable x, and then we'll evaluate the definite integral. So we draw a right triangle. Here's theta. We know that x is equal to 1/2 tangent of theta, which of course this is the same as saying that the tangent of theta equals 2x. So this side is going to be 1, this side is going to be 2x, and using Pythagorean theorem this will be 1 plus 4x squared. So what we're going to get is the following: 1/4 times the square root of 1 plus 4x squared. This, of course, right here is a secant of theta times a 2x. This 2x here is just the tangent of theta, plus the natural log of the absolute value of the square root of 1 plus 4x squared. That, of course, is the secant of theta, plus 2x, that, of course, again, is just the tangent of theta. And now I'm going to evaluate this thing between 0 and 2. So I'm going to end up with 1/4 for square root of 17 plus the natural log of square root of 17 plus 4, which, of course, this is approximately equal to 4.65, which was the arc length that we found when we first learned about arc length.